Okay, so today we have Karyn speaking. She asked me to tell you all that she is in fact originally from France. In case there's any confusion, she got her PhD from Ecole in Paris and then a postdoc in Zurich. And after that, she was an assistant professor at Sherbrooke University before moving in 2006 to Yale. And this past year, longing for the homeland, she was returned to France, is now in Ecole Polytechnique in Palaiseau. So for those of you going to ICAP this summer, you have an opportunity perhaps to visit those Ecoles. And she's an expert in really many-body theory, and this is branched out into a lot of different physical systems. So conventional systems, cold atom systems, and we'll hear about today optical systems, and also from time to time quantum information. So, Karyn?
Yes. Thank you very much. So what I would like to do is to give my own point of view. So I'm sorry, I will try to talk about this work, many-body quantum physics with new kind of very nice particles, photons. I'm not called atoms today, but what we would like to show is, in fact, maybe we can play a similar game with light and try to reach new states of very nice matter, such as a Mott state, may be interesting. So here it is a goal. So what I will try to talk about is a few works. The first part of it has been done with Jaynes-Cummings, that was at Yale at the time as a postdoc, and then still Gervin entered into the game, and I will talk about that work. And I will try to talk this very beautiful graph here, which is how can you simulate H states of light that can go along one direction. And so, I mean, this is a beautiful work that has been done by the student Alex Petrescu, and this has some link with applications that I will try to show. And of course, there are some links to what is going on here. And more precisely, I will try to show the following things. So I will just introduce a nice model that one can build with an array of so-called waveguides. So you could imagine that you get an almost one-dimensional waveguide, and you can really couple them. And the main idea is to build an array which can have a form which is square lattice, but it is perhaps better to have this honeycomb shape because the electric field can really leak in a nice way from one waveguide to another waveguide. So the first thing that I would like to talk about is a Jaynes-Cummings lattice model, and I will try to show some link with cold atoms and with a model which is well known, which is a Bose-Hubbard model, and is quite nice because you can have two very nice phases. A superfluid phase of here photons. It means that the wave will be delocalized over the full lattice, and a Mott phase of a photon. And here we have to say, what do we mean by a Mott phase of photons? Then, what I would like to show is that now there is a beautiful idea that maybe one can play around and look at so-called artificial gauge field with so-called neutral particles. So of course we cannot explore the Arnold-Bose effect because here we have light, we have neutral particles. So how can we simulate such an artificial gauge field? And here there are many ideas that float around with cold atoms. But what I would like to show is maybe we can do that with photons, and I will show how point of view on that, and it has some link with some work which is done here as well. And then what I would like to talk about is a kind of a Kondo effect. So maybe some of you heard, I mean, what is a Kondo effect with a fermion? And I would like to show that one can realize a photonic Kondo effect, and I will talk about this in more details. So let's start with things which are maybe simple and maybe you heard. So we start with this Bose-Hubbard model. So we have boson on the lattice, and the boson can hop from side to side with a hopping amplitude J. And of course, this would give rise to a well-known superfluid phase, as we all know. but then the main idea is to drive on some new state of matter due to interactions. And for cold atom or the older so-called Josephson junction arrays, which is also a beautiful, very nice system, people have shown you can engineer this Hubbard type coupling. And this Hubbard type coupling, as we all know, give rise to Mott phases, because we pay a price when we try to add two particles at the same site. And I mean, what is really nice is that it is a simple Hamiltonian we can think about, because we have only two parameters, right? J and U. But of course, with cold atoms, something which is very nice, I think, is that we have the third axis, and which is very important, which is mu, which is the so-called chemical potential. And we can really tune that with cold atoms, because you can think that you have this beautiful so-called harmonic trap, and really you can pass from a Mott lobe with one particle per site, and you can enter in a superfluid phase and then go to a Mott phase with two particles per site. And so cold atoms, I think, are really nice, in my opinion, because first, I think it is simple to build a very nice optical lattice. So, I mean, this is an important point. Second, you can really tune U and J. But third, you can play very nicely with the mu parameter. Okay? So now the main idea is, how can we engineer that with light? As I mentioned, maybe we can imagine we have some waveguides, and light can leak from one waveguide to another waveguide. And if we think about a waveguide as a simple one-dimensional so-called transmission line, then we have a short waveguide, and essentially we keep one mode of light in a so-called quantum sense, and this mode can leak from there to there. So at a general level, we imagine in a simple way that we can really build this term with light. As soon as we get one mode of light per waveguide, then I and J here would mean waveguide index, okay? But the point which is difficult with light is, how do we build this Hubbard interaction with so-called photons? So how do we do that? And I mean, this is really the point that we want to address. So maybe you have some ideas. We could play with the medium. We could have some non-linear so-called cavities, and indeed you could perhaps induce such a term. But maybe you can have another way. Maybe you can play with light-matter interaction. And this gives rise to the Jaynes-Cummings lattice model that I want to talk about. So main idea is that we have an array of waveguide, and we want to put some light that goes through, and now we have some two-level atoms or some two-level qubits inside. And as I mentioned, I mean, it seems very maybe not simple to build, but you can have a look at the website. And last month came this very nice work where now they can build with this circuit QED. So those are superconducting strip lines, and now you can really couple them in a so-called capacitive way through this kind of so-called junction. And at a simple level, the capacitive coupling between waveguide gives a hopping between the photons. So now they can do that. They can actually build an array. And next step would be to look at a qubit inside the waveguide. So of course you can think about many different cases, right? You could have some atom with many so-called states. Here we want to look at a qubit, so two states. And the model here that we will look at first is the Jaynes-Cummings model. So you have the two-level atomic state, Omega means the so-called detuning between the two states. Here you get the so-called frequencies of this mode light, and now you imagine that you can absorb a photon and you can pass from ground state to the excited state for the atom. Okay? And here what is important, we will neglect, so Jaynes-Cummings, we will neglect the term which are of the form sigma plus A dagger. Okay? But a priori, if we look at the so-called dipolar coupling, we should in principle keep the full so-called sigma X coupling that would couple to A plus A dagger. But the Jaynes-Cummings model here, we just neglect this term, assuming that G is smaller than these two frequency parameters. Okay? So, of course, for one waveguide, this is well understood and since a very long time. And what do we want to do here? We want to exploit the photon blockade physics to realize the equivalent of a Mott insulator. What does it mean to have a Mott state? It means that I have a lattice, and per site I have exactly one particle. Okay, and if I try to put one more, it costs a price, it costs a gap. So here we want to explore this idea. And how does it work? If we think about the atomic limit, so very weak coupling between waveguides, we have to solve this Jaynes-Cummings model. Okay, so first let's put G equals 0. We get some state. A ground state means no photon. So it means the so-called vacuum state. And atom is in the ground state, downspin. Okay? Now the first excited state, if we assume this equal to that, then we can have one photon and atom in the down state, or we can flip the atomic state. We can go to the up state and have no photon. Okay? And we can do that. And here we see that we can send light and we can pass from the first excited state to the second excited state to the third excited state. Okay? So we can do all things we like. But as soon as we include the coupling with light and matter, we have to solve a 2x2 matrix. Because here we get a spin half particle, so we have to use a 2x2 matrix form. We can solve the eigenenergies, and what we get is we get new state. We see that we form now this Dre state, because there are states that so-called combine the states that we had before. And those are the Dre states or the polariton states. And now you see what will happen. We try to send one photon, we can't. But we can't send two, because now we don't find any states there. So somehow we can play with this idea that we can couple light and matter, and we can use the photon blockade as a pseudo-Mott effect. It means that I can build a state with just one Dre state in a waveguide. And this Dre state is really a Dre state between light and matter, right? Because we entangle the two, right? But we can't add a new photon. We have a photon blockade. So we can see that as a pseudo-Mott effect, okay? So now we want to use this idea, and this has been looked at by many groups, and I should mention many works, at least at a so-called theoretical level, still. But main idea is now we have arrays of waveguides, and inside we have one qubit. Here we place the qubit here, but we could place them there, I mean, it is okay. Main point is we have two terms that are important. The hopping terms that I mentioned, where light can leak from one waveguide to next waveguide. And now we play with the Jaynes-Cummings term, G, to simulate the Mott state, the Mott physics. But here you see the point. I have added mu, the so-called chemical potential. But you should tell me that for light, it does not make much sense, right? Because we don't really know what is mu. So right now, let's keep mu as it is and think that we would work in a ground so-called canonical space. And then we need to explain how we would simulate mu in a lab. But for now, what I want to do is to keep mu here and to couple mu to the real quantum number. What is the real so-called quantum number? Here it is the so-called polariton number. It means that the good object which so-called commute with the Hamiltonian is the number of so-called photons, the total number of them, plus the total number of atoms. Okay? So, at a very general level, let's check that we all follow. We said when kappa is 0, here, so-called kappa, it is a J for so-called cold atom, so it means hopping from one waveguide to next waveguide. Okay? So kappa goes to 0, we have the Jaynes-Cummings model, and we solve the model, we get these eigenenergies. Because we get a 2x2 matrix, we get two branches of excitations. The plus and the so-called minus branch, and small n means a state with a fixed dress state number. Okay? Now you can really see that the branch that causes the less energy, if you fix small n, is so-called minus branch, because here we get so-called positive number. Therefore, the branch that causes the less energy for a given n is the so-called minus branch. So now we can virtually play with the so-called parameter we have. So again, here I plot things as a function of mu. But in a lab here, the real challenge will be to claim how we can really realize mu. But okay, so let's look at as a function of mu. And the first Mott lobe, it is very simple. It is the vacuum state. Then the next Mott lobe has one dress state per waveguide. And this is an interesting state. Now, if you just compare with the cold atom and Bose-Hubbard model. In Bose-Hubbard model, I'm sure you are all used to see the Mott lobes, which are very similar. It means that you take the Mott state with one particle, with two particles, with three particles, with four particles, and they have the same shape. At least here they are equidistant, right? But with the Jaynes-Cummings ladder, the thing is, here we get some so-called function of n here. Therefore, you see that Mott lobe with one dress state has a large phase space. But as soon as you want to put 2, 3, so on, they become very, very narrow. Okay? So here it is a main point. But first thing is that a priori in a lab, if someone could imagine to tune this mu, one could realize maybe a Mott state with precisely one dress state per waveguide. And it is a nice point, I think, that maybe someone could do that. Then we said we take the other limit. We have a very large hopping term. Then we solve the type bending model. I don't want to enter much into things here, but the main point is that you take a simple lattice and you find that the band so-called structure has a real minimum at k equals 0. And therefore, the boson would fill the k equals 0 state And one would find a very nice kind of B easy ground state. It means that the boson would be in a k equals 0 state, and in a so-called real space, it would be completely delocalized. So at a general level, of course, here I take a very simple limit, where G is completely 0. But based on this very simple argument, we can guess that if someone could tune kappa or G, maybe one can reach two different phases. Okay? Superfluid phase of light and Mott phase of light. Now maybe I need, for so-called theories to are here, maybe I need to say that now you could ask me, what about the phase boundaries? And in fact, you can really build a very nice 5-4 theory, like in your usual statistics class. I mean, we learn to build a 5-4 theory for the Ising model. Here we learned how to do that for Bose-Hubbard model. And we can do that here in the same way. It means that the main idea is that you want to start with a mean field theory. The mean field theory means that you just decouple the opinter, right? So at a so-called general level here, we just decouple this term like that. And here you see that we fix the superfluid state to have a fixed number of AI operator, like in a usual B EC sense, to be non-zero. Okay, so let assume we can do that. Now we do that, we get an order parameter, which is this psi order parameter, and then we can really solve things because we get a local we get an atomic. And I don't want to enter much into so-called detail, but you can really do a simple so-called perturbation theory from that Hamiltonian, and assume you are very close to the phase boundary, so psi is small, and you can really nicely build this 5-4 theory. So here we can check that we have a second order so-called phase transition, because U has the right side. And the phase boundary, as in the usual second order so-called phase transition, should obey that R equals 0. So what we have to do to find the phase boundary between Mott phase and superfluid phase is just to solve R equals 0. But of course, this depends on all the parameters we have in, but we can do that. And at the mean field level, we have a phase diagram, which is like that. Yes? Victor, yes?
Yeah, I have a question. So if you have general kappa and G, what is the quantum statistics of the particles in this lattice model? So in principle, you have bosonic commutation relations and spin commutation relations. So how do you know that it's
very
bosonic?
Good point. So if you let me, I will answer in a 2 slides. But this is a very important point. And I am glad that you asked this point. Yeah. I mean, this is a very good point. So here we just look at the most, a simple thing. First, we want to build the phase boundary, and we build this 5-4 theory. Now we have these so-called phases, and we like this Mott block with 1 rest state per waveguide. Okay? But first, you should tell me, we are in 2 dimensions. We know that mean field in 2 dimensions is not good enough, so maybe we should do better. And indeed, we can do better. So 1D, you can do a very nice D MRG, and you find this Mott lobe, which has a curse behavior. And this curse behavior, it is like in a Bose-Hubbard model. You get a so-called KT phase transition. So K means the coastal and T a southwest phase transition. In 2 dimensions, you can use many tricks. Strong so-called coupling approach, so-called quantum Monte Carlo, many so-called the cluster approaches, many things. And you can find this Mott-Lobe, which has a nice shape. So here is a midfield approach, and here you just do a strong coupling expansion, and here you find a nice Mott-Lobe. So what I want to say here, of course, the shape of this Mott-Lobe depends on if you are in 1D, 2D, 3D, but still you have different phases, okay? So first important point. Second point that we could think about, in a Bose-Hubbard model, we all know that we have points which are very special. Points at the tip of a Mott-Lobe obey a particle-Hall symmetry. It means that, here it means that you can really exchange space and time. And the dynamical critical exponent, Z is 1. So now you could ask me, do we found this point at the tip of a Mott-Lobe? And indeed, yes, it is still close to this Bose-Hubbard physics. I don't want to enter much into details here, but main point is that you can build an exact argument based on symmetries. And the main idea is that you can build the partition function of the full system. You have photon modes, and as spin become vector on the block sphere. And you can exploit symmetries in a very nice way, like for Bose-Hubbard model. First, you can decouple the hopping term in a very nice way through a Hubbard-Stratonovich scheme, and now you enter into the game this psi mode, which is just the mean field order parameter. Okay, so let's do that. At a general level, to build a psi 4 theory, the hard aspect is to integrate out things that we don't like. So we need to integrate out the A mode and spin mode. And at a very general level, here, this is very difficult. Because spins, they have the very phase, they are difficult objects. But still, we can really exploit symmetries. So here we start with first. If we are close to a phase boundary, we know that psi would be a small object. So we can expand the action in that form. And there you find the R term, but now R tilde would be the exact location of this phase boundary. Okay, so at a general level, because close to the phase boundary psi is small, you can still find such an expansion like that. But at a very general level here, what is really hard is to say what is that, K3, R tilde, and U tilde. Here it is a very hard task. But still we can look at symmetries. And we start with the Jaynes-Cummings model. We have human symmetries. And we can use a very simple spin rotation into the plane. And we can show that the action would be the same if we change A into that form, psi into that form, and N into that form. But if we do that, the price we pay, we have to change this mu with a so-called dynamical phase. So at a general level, suppose we change A into that, A psi into that, and N into that, and mu into that. Then you ask, how should I choose K1, K2, blah, 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 such that the action remains the same? And then, like for the Bose-Hubbard model, you find these rules. K1 equals that. But then, it implies that at the tip of a Mott-Lobe, this is 0. Because in our case, what we look at here, we have the phase boundary, which is r tilde equals 0. And now we look at the function of mu. So at that point, the slope is 0. Therefore, it means that this is 0. So based on very, very general argument, one could show that at the tip of a Mott here, we still have a particle hole so-called symmetry. But here it is more subtle to interpret that. So first, about the phase diagram in 3 dimensions. So now we can build a phase diagram because we can play with the third axis, which is delta. And delta is the detuning between the photon frequency and atomic state detuning. So at a general level, we get this 3D phase diagram where these phases are Mott state with a given number of gray state, and this, so blue mean superfluid lines, and now the red lines mean lines where you get a particle hole symmetry. So the Z exponent is 1. Okay? Now let's come back to your nice point. What about the particles? So in 1D, we have shown that you can really map things onto a spin chain. And when you go to the superfluid zone, but you are very close to 2 Mott state, this so-called boson, you can really show they are hardcore boson. Okay? Now, if you are far away from a Mott law, this boson would go to free boson. But so at a so-called general level, we can really look at these 2 cases. Then we try to build an exact mapping, not in a so-called photon state, but in the dress state so-called approach. But then it is very hard to pass from this hardcore limit to the free so-called boson state. So this has to be done in a so-called nice way. So we work on that, but up to now there is no work that shows how do you pass from hardcore boson to free boson. Okay. So still you could play with being at the tip of a Mott lobe, and then you could build like in a work by Altman and Daimler, you could build a spin-1 chain because you can just keep 3 states. Here it means the 3 Mott lobe state. Okay? But still, it is still an open work to show how do you go from hardcore to free so-called boson. The thing that we need to work on still is how you can break the U1 symmetry, because a priori the real coupling between light and matter would be Z2. U couple a sigma X operator with A plus A dagger mode of light, which is the electric field. And this we work on that, but maybe you can get a new phase diagram with a new state here, which is not Mott state, but which still have a gap. So this is still to be done. So at a so-called general level, so from theory point of view, if someone could build this arrays, so now they can build that. The real challenge is to go to a state of matter that would be like a Mott state, or at least show a kind of gap. I think the main point really is to be able to mimic the chemical potential for photons. Then, as soon as you have a Mott state, which seems to be hard to do, because again you don't have the trap here. Then I think things could be done because you can play with with a 3D phase diagram, you could imagine that you tune this delta axis and pass from mode to a superfluid and measure the psi object, which means the expectation value of superfluid or the parameter. But at a very general level, here I talk mainly about the equilibrium of the. But really here, I mean, what I like is we have really a non-equilibrium problem, because we should drive the lattice with some AC signal, so and send some photon. So at a very general level here, it is a very nice field to play with nice idea for non-equilibrium physics.